So I'm going to briefly talk about belt drives. This is sort of the last part of Simple Machines belt drives. It's another type of simple machine, if you like. And what you're seeing on the screen there, hopefully you can see on the left-hand side, you've got a small pulley at the bottom of the picture, if I highlight it in yellow, and it's driving this much larger pulley here. So we've still got our terminology of drivers and drivens that we had in gears, or driver gears, driven gears. We've got the driving pulley and the driven pulley here. But it's to do with belt drives. And actually what you're seeing there is what's called a multiple belt drive, and it's actually a V-belt drive, and we'll discuss them briefly in a moment. So a multiple belt drive with those things you see in here are grooves in the pulley, so the belts sit in the grooves there. That's another diagrammatic picture of a V-belt drive, again showing you 3 belts in this system. Motors driving on the smaller pulley here onto the larger pulley. That's probably like a machine tool there, it might be some sort of generator or whatever that is driving there, and this is the electric motor down here driving the smaller pulley here. So there are V belts, and there's 3 of them. The more belts you have, the more power you can transmit and so on. And again, I don't know if you've seen this in the workshop at college, if you ever looked at the pillar drills, you still sometimes see pillar drills. If you look at the top of the pillar drills, there's a belt there behind a guard, and that belt is running on these pulleys here. You've got sort of cone pulleys here, they're called, and by moving the belt from one set of cone pulleys to the next set, you can change the velocity ratio of the belt, and so you can change the speed of the drill by changing the belts onto different pulley arrangements here. So that's changed the velocity ratio. So you see them all around your belt drives really. So belt drives, they're employed to transmit torque between shafts, where one shaft is doing the driving, turn the driver if you like, another shaft is turn the driven. Belts can be made from a variety of materials, and as I said, traditionally it used to be leather, but nowadays it's more like a reinforced elastomer material, such as a synthetic neoprene rubber with nylon, and sometimes it can be a metal reinforcing fibers as well. So the technology involved in the belts now is quite advanced, and the belts are quite specialized piece of equipment. You buy belts, you don't make a belt for a belt drive. There are many types of belt drive that's in general use. There's what's called flat belts, and there are V belts. There are round belts. They're sometimes called rope belts as well in some textbooks, I've noticed. And then we've got what's called tusked and notch belts. Sometimes see the tusked belts in timing belts on cars and so on. Flat belts, they run on crowned pulleys. They're actually slightly curved pulleys. And V belts, they run in groove pulleys. And then tuft belts, they run in tooth wheels, or what's called sprockets sometimes. So quite specialist bits of kit here we're talking about. It's a bit like gears. You kind of buy in gears. You don't make gears in here. You sort of buy in belts and pulleys and so on. You don't normally make them yourself. They're kind of bought in items in a lot of cases. Overview belt drives here. They're used mainly for transmitting light loads because they sometimes can slip, but they're very flexible and they're suitable for applications where there's a slight misalignment between the shafts, because you sometimes get this in manufacturing, but they will accommodate that quite nicely if you do have a slight misalignment. Flat belts can also be crossed to give opposing directions of rotation. That's kind of what's showing up here. You can see that the belt is actually crossed here, so the direction of the output is actually changed. If it wasn't crossed, obviously it'd be the opposite way to what's showing there, but crossing the belt drive, you can change the direction of the output. And belts can be twisted to connect different shafts that are not in the same plane, and that's what we're trying to show here. We talked about bevel gears, if you remember, in our previous lecture on gears, where we could turn the drive through 90 degrees, like in an egg whisk or in a hand drill. And you can do the same kind of thing with flat belts. They are very flexible, and this drive is sort of showing you it's changing through 90 degrees by twisting the belt. You can only do that with flat belts, but it can be done, which is quite useful. Applications, again, you sometimes get questions that say give an application of a flat belt and so on. They're used in all sorts of different applications. I've got some here: plant pump equipment, compressed air equipment, heating, ventilation and air conditioning systems. They're used in many different applications, so just mentioning one of them would be good enough for you. So V-belts They transmit greater power than flat belts. So if you want more significant power applications, then you would move to a V-belt. And that's because of the increased friction effects you get because of the V-belt shape. So it's got this shape here, this V. That's where it gets its name from, the V groove there. And because it's in a V, it actually generates more friction. And because it generates more friction, it generates more torque and then more power. So more than 3 times the grip of a flat belt for the same material is often quoted as a factor. So they're certainly preferable if you've got a more rugged type of drive required. Belt drives run in grooves and can operate at high speeds. Of course, that's one of the problems with V-belt drives. Obviously, manufacture a bit more complicated. You've got to manufacture these grooves in the pulleys and so on. But one belt drive can replace multiple flat belt drives or wide flat belts, so they can be quite beneficial on a space consideration. You see them often in machine tools in industry. Automobiles would have them, washing machines would have them, tumble dryers, and pillar drills, as I mentioned earlier. Pillar drills use V-belts if you look at them, but they're normally V-belts, not flat belts. This is tooth belts. Synchronous belts, I've seen them also called. So tooth belts or synchronous belts, they run in on tooth pulleys, and they give a more positive drive and are used where slipping would be detrimental. One of the problems with all belts, whether they're flat or V, is they can slip, and of course that can lose drive. So sometimes you get detrimental effects on components if belts slip. You be careful of that. So synchronous belts have a similar power capacity compared to V belts. Applications would be in the camshaft on automobile engines, I've mentioned before, where slippage can be problematic for the valve timing and possibly even result in damage to the engine itself. So that's where you kind of use the tooth belts. So advantages of belt drives. First of all, no lubrication is required or desired. Actually, you don't want any oils between the belt and the pulley. You do need, obviously, lubrication at the bearings of the pulleys. You would need it there. But for the belt itself, you don't want any lubrication, so there's no lubrication required. And generally speaking, the maintenance is minimal with belt drives. Once they're up and running, you can kind of leave them alone, really. They offer this automatic overload protection due to slippage. Now, that's one of the things that's a friend and a foe, really, because when you do get slip, you lose drive, so that can be problematic. You might not want to lose drive, certainly on a machine tool. On the other hand, if there was a problem on a machine tool whereby somebody, say, has set up a cut to take off the material, and it's a massive cut, and it's obviously going to be detrimental to the machine, in that case, you'd rather the belt slip. You get a smell of burning rubber, but the belt would slip, and it would prevent the machine tool from taking a very large cut, which might cause damage to the machine tool. So it's a sort of friend and a foe. Automatic overload protection depends on your perspective there. Purchase the belts in standard sizes, and they're easily adjusted. I've never done this myself. I've never been involved with belt drives, but apparently they are very easy to adjust if you want to adjust them for your particular situation. You buy a standard belt and then you adjust it to suit the actual configuration that you're designing or you're assembling and so on. They're quite easily geared because you're just using different size pulleys, like with the cone pulleys on the pillar drills I showed you a few slides back. It's very easy to move them between the different cone pulleys, and then you can just change the mechanical advantage, the velocity ratio of the pulley system. So it's quite easy to gear with pulleys. They have reduced noise and less vibration, so you often use them in industry where you've got, say, grinding machines where you want a very, very fine surface finish, you hone in the surface finish, and if you use a gearbox, you might get more vibration, which might show as chatter on the machine surface. But belt drives, they run very smoothly, very quietly, very smoothly, so they can be beneficial for those kind of machine tools. They reduce the vibration. Okay, so smooth running, it says there also. Less vibration in the operation. So for machine tools, that's particularly useful. So disadvantages here, we've got the maximum pulley ratio is tendency to be 3-to-1 ratio. Now, when you look at the belt drive, if I go back to my slide just for a moment, what they're saying is the ratio between that pulley and that pulley was 3-to-1. This should be no more than 3 times that pulley is what they're saying. And they're saying that because of the angle of lap would start to decrease. That angle of lap there, where the contact with the belt with the pulley, it gives the friction. And the smaller the angle of lap, the less friction you get, so less torque and so on. So the bigger you make the driven pulley, then the smaller the angle of lap would be in this case. So they recommend a ratio of 3-to-1. Obviously with gear drives you can have much, much bigger ratios with no problem with compound gear trains we looked at previously. Repeated flexing causes failure. You've got to think of the belt. The belt is going around a pulley and it's also in tension, so it's suffering from tension loads, it's suffering from bending loads. So that does eventually cause failure of the belt. And you can get small power losses due to slip and creep. Slip obviously is where the belt is slipping on the pulley. Creep is where the belt actually starts to get slightly longer. And so that actually reduces the tension in the belt and that affects the drive characteristics. But modern belts, generally speaking, are quite good from a creep perspective, especially if they're reinforced elastomers. Then they tendency not to creep too much. You can get location problems because if you want multiple belt arrangements, they can be quite wide in their design. And so sometimes that might be a problem. It might be just a constraint problem on the environment you're trying to put the belt in. So again, that can be a problem. That belts are not easily repaired. You can't really repair a belt. And wear of the belts and, of course, the bearings can reduce tension, and so they need retightening. So a little bit of maintenance there, not much, but sometimes you need to go in and retighten things to make sure you've got the initial tension correct. Adverse service environments. So extreme temperature ranges can cause problems for belts. High moisture can affect the belts. Oily or chemical field atmospheres, they all kind of affect the belts. They can damage the belts, they can cause slipping and so on. So more so affected by environments than, say, a gearbox would be, for example. So again, I've given lots of disadvantages there. You would only need to remember a couple of them for the assessment, okay? I'm just going to show you this formula. There's a couple of formulae in your formula sheets related to belt drives, but this all you've got is a mechanical advantage formula, and there is a velocity ratio formula, which is the inverse of mechanical advantage formula. And I've just shown you an example of a question that has cropped up in an exam a few years ago now related to using mechanical advantage. So I'm just going to show this to you and let you do one little example. So in example 1b, we've got a flat belt pulley system that's shown in the sketch. We've got to determine the mechanical advantage, so the MA in this case, given the diameter of the driver pulley, they've called that little d here, of 250 millimeters, and the driven pulley diameter, capital D, is 500 millimeters. So the formula is given to us, mechanical advantage, defined as the diameter of the output pulley divided by the diameter of the input pulley. Kind of load over effort if you go back to our mechanical advantage formula. So to work that out, mechanical advantage is a big D divided by little d. So from the question, that's 500 millimeters divided by 250 millimeters. So mechanical advantage of 2 in this particular case we're looking at. So example 1b, perhaps you just have a quick go at this. Got to calculate the mechanical advantage again of the V-belt pulley system shown. The motor pulley, which is a smaller pulley, has a diameter of 300 millimeters, and the larger driven pulley has a diameter of 1.2 meters. You've got to work out the mechanical advantage. Can I let you do that for a moment? I'll show you my solution because it's very straightforward, this one. So mechanical advantage would be the diameter of the output pulley, and they stated that in meters here. I put everything here into millimeters, so 1.2 meters is 1200 millimeters, and that's divided by the input diameter pulley of 300 millimeters. So the mechanical advantage we're given is 4 here. Okay, so very straightforward calculation. A few further exercises related to belt drives. So exercise 2b. Given that the driving pulley, labelled A, has a diameter of 800 millimeters and the pulley system's mechanical advantage is 2.5, we've got to determine the diameter of the driven pulley, labelled B. The answer is shown as 2 meters here in brackets. I would encourage you to stop the presentation and attempt this question. As a hint, you will need to make use of the formula given in the formula sheet. We're considering here mechanical advantage, so we'll be using the mechanical advantage formula, which is diameter of the output pulley divided by diameter of the input pulley. So thinking through the question, we're given the mechanical advantage in the question, and we're given the diameter of the driving, that's the input pulley, so we can rearrange the equation to find the diameter of the output pulley. I'd encourage you to stop the presentation and attempt this question, but the full solution is shown on the following slide. Exercise 2b, here's the solution. We're given in the question the diameter of gear wheel A, 800 millimeters. We're given the mechanical advantage, 2.5. We know the formula for mechanical advantage from our formulae sheet. So stating the equation for mechanical advantage and rearranging the equation to make the diameter of pulley B the subject, we multiply both sides by the diameter of pulley A in this case, so MA multiplied by DA. Then to calculate dB, it's 2.5, the mechanical advantage, multiplied by 800 millimeters diameter of pulley A. That gives us 2000 millimeters or 2 meters. Exercise 3B, more complicated question here. A belt and pulley system has an input pulley and an output pulley where the output pulley is 400 millimeters in diameter. If the input pulley turns through an angle of pi upon 6 radians and a point on the input pulley's circumference moves through an arc length of 78.5 millimeters, we've got to determine the velocity ratio of the belt and pulley system. So this is a slightly more complicated problem, and it involves some background knowledge from our mathematics unit. So as a hint, we need to refer to radian measure, something we covered in our mathematics unit previously, related to arc lengths of a sector of a circle. The arc length is shown here, labelled S in this diagram. We're also in the question given the angle subtended, shown as theta here, which is pi upon 6 radians. So using our radian measure formula, S is equal to R multiplied by angle theta, where R is equal to the radius of the pulley, which we're trying to find in this particular case, because we're actually given the diameter of the output pulley. So transposing the equation for S equals to R theta, we can find the value of R. We can then find the diameter of the input pulley. So once we've got the diameter of the input pulley, I noted that in the question we're given the output pulley diameter, which is 400 millimeters. We can then find the velocity ratio from the formula given to us in our formulae sheet. I encourage you to start the presentation and attempt that question, but the full work solution is shown on the following slide. Exercise 3B, here is the full work solution for your reference. As always, try and extract the information from the question, use appropriate labelling as required. And the first step here was to find the inner pulley radius. Second step then was to find the inner pulley diameter. And then the third step is to find the velocity ratio given the formula stated. You should find the velocity ratio is 0.75.